Hey guys, welcome to All Electronics. I'm Gregory, and today we're gonna take a look some data I got characterizing this little mixer here. It is an active mixer with a BJT transistor. We have here the schematic, and I assembled this mixer here to test and to see how the mixer works and how is the performance of the mixer with different input powers. And here we're gonna see how the 1 dB compression point works, the third order intercept, how to measure it. But first, let's take a look here at the circuit. So guys, the circuit is assembled here. I can make another video about this in the next video. But here we have the diagram, and we can see that we have here a BJT transistor in the center. Here is the active device of the mixer. And how an active mixer works, guys. We inject the LO power in the emitter, and we inject the radio frequency power in the base of the transistor. What happens is that the base emitter junction will see the difference between the LO and the RF, and the transistor will be excited by the two powers, the LO frequency, power frequency, and the RF power frequency. For the LO, the transistor will behave like a common base stage. We can see that for the LO signal, we are injecting it in the emitter, and the base will be grounded for the LO. So we have a common base stage. And for the radio frequency power in the base, we have a common emitter stage. It's very easy to see here that we are amplifying the RF signal with a common emitter stage here, because we will consider that the LO is grounded for the RF power. So we have the transistor operating in two different ways for the LO and the RF. But what is important is we are injecting the difference between the LO and RF in the base emitter junction. And as the base emitter junction has an exponential relation, the collector current has an exponential relation to the base emitter voltage, we're gonna have a lot of intermodulation, because when we expand the exponential function, we have a lot of terms in the Taylor series, and one of the terms is a quadratic term, and the quadratic term is multiplying the two signals, LO by RF, because we're gonna have RF minus LO squared. So we have the multiplication of the two signals, and this is the mixer action. The square term of the expansion of the exponential relationship between the collector current and the base emitter junction is what gave this stage the mixer characteristics. And this is why this stage works, because we have a term in the relation between the current and the base emitter voltage that is squared, and this is the multiplication factor that will multiply the two signals. So first thing we see is that at the output here in the collector, we are using this choke here and these two capacitors here to make a resonant tank over the IF frequency. So we're gonna have a higher gain only above the IF. We can see that we're gonna have here in the collector a lot of terms. And this is why this active mixer here is used more when the IF is a lower frequency than the LO and RF, because a band pass filter or a low pass filter at the output can filter out all the other harmonic terms generated by the exponential relation between the collector and the base emitter voltage. So we can see here some details of the circuit. Here I draw this transformer backwards, but this transformer I'm using to match the impedance of the 50 ohm LO here to the emitter of the transistor, because the emitter junction here, seen from the emitter side, will be very low impedance. So we have a 5-to-1 transformation here to decrease the impedance of the LO to excite the emitter junction. The RF here I'm injecting directly on the base, and we can see that the output circuit is a bandpass circuit, and here I am tapping the IF in the center tap of this capacitor divider here, so we can transform the impedance also. So here the collector is seeing almost 2000 ohms, and we can transform the impedance to a lower impedance here to the IF using the capacitor tap. And this is important, guys, because in this configuration the bandwidth of the output filter here, the resonant filter, bandpass filter, will be I don't know how to say that, will be inversely proportional to the impedance seen by the collector here. Okay, guys, so what I did here, let's go to the data. I talked a lot here. Let's get my head smaller here. Okay. So first thing I did, guys, is a sweep of the RF power using a constant LO here, 7 dBm, and also a sweep of the RF power using a constant LO of 10 dBm. This is important because we can plot these two curves here. In blue we have LO entering, so we have the LO entering at 7 dBm, and we're gonna sweep the power of the RF, and we're gonna see the power of the output here in the IF frequency. And after, we're gonna change the LO to 10 dBm to plot the orange curve here. We can see, guys, that for a 7 dBm input power in the LO, exciting the input power if the LO with 7 dBm, we have almost no conversion loss. We are in the input here, we have minus 15 dB, and the output minus 14.8 here. So we are almost one to one here relation, and we can see this here. So this is the conversion relation, and when we increase the LO to 10 dBm, we have conversion gain because it's an active mixer. So increasing the power of LO here, we are exciting more the base emitter junction, and we're gonna get some conversion gain. And here we can see the conversion gain, guys. We are inputting in the system minus 15 dBm, and we are getting on the output minus 9 dBm. So a 6 dB gain. Very interesting. But you're gonna see that this is not magical. We're gonna lose some in other aspects when we increase the LO power to get more gain of the circuit. A very important thing to understand, guys, is that here for lower powers, we are working in small signal. So we can see here, guys, that in this region here, the transistor is working in a small signal perspective. We have a linear model of the active mixer, and we are working here in the linear model. When we start to increase a lot the power in the RF, in the base of the transistor, we start to go to compression. And the compression in radio frequency is the point where our small signal model don't work anymore. We are losing the small signal model, and we are entering a large signal behavior of the circuit, because now we are saturating, we are generating harmonics. Our input power now is not going to the IF, is going to other harmonics of the system. And this is why we are getting lower power as we increase the input power. This is very interesting, guys. This is very interesting. So you can see here we have linear a linear working principle, and as we increase the RF power, the signal start to compress, the gain start to drops. And we can see here, guys, we have linear a linear working principle, and as we increase the RF power, the signal start to compress, the signal start to compress. And as we increase the RF power, the signal start to compress, the gain start to drops. And And here comes our first parameter of the mixer, the 1 dB compression point. That is the point where the actual gain of the circuit drops 1 dB below the linearized perfect gain of the linear model. So if you extrapolate the linear region here, we can see that in some point our actual gain drops by 1 dB. And this is the 1 dB compression point, the point where the output is compressed by 1 dB. And we can see this here. So how we can compute the 1 dB compression point, guys? First, we get the first data points here where the system is working in linear region. So we have here the first 6 data points, and here also, that are these first 6 data points here of the table. So we have these 6 points here and 6 points here. And I copied that to this table here, guys. And this is the signal, is the small linear part in the lower power region. So guys, we decrease the signal by 1 dB. So I subtracted from the signal. We can see that we have an offset here of 1 dB, okay, because I subtracted 1 dB. So here we have -9, and here we have -10. Here we have -7.7, here we have -8.7. We can see the formula here that we are subtracting 1 dB. So now we have this region here, the linear region of the mixer, with a 1 dB decrease. And now we can extrapolate this curve using a linear extrapolation. So when we extrapolate the linear model, we have the theoretical linear model, and we can see exactly where the linear model will intersect the real system. And we can see here in the blue curve here we have an LO power of 7 dBm, and we are intersecting at -3 dB. So when we are inputting in the mixer -3 dB, we have a drop, is the point where we have a drop in the gain of 1 dB in respect to the linearized perfect model, theoretical model. So the 1 dB compression point for a 7 dBm LO signal is -3, this intersect point here. So this is why I put here -3 dBm. But when we are exciting the mixer with 10 dBm here in LO, we know that we have a conversion gain. Now the system is working with conversion gain. This is good. We have gain in our mixer. But we can see, this is very interesting, guys. We can see here that the 1 dB compression point is before. The 1 dB compression point here is -7 dBm. We can see here I put it -7 dBm. So the signal will compress first using more power in the LO. And this is because when we increase the LO power, we change the transistor bias. And now the transistor is working more in a large signal, behavior, because we are exciting more the non-linearities. And this is showed here by the 1 dB compression being less, being first before. And this is telling us that when we input 10 dBm at LO, we gonna have an output with more harmonics. So the mixer is working in a less ideal way, because in ideality, a mixer is a system that multiplies the two signals that have only the square term. But when we are exciting with more power in the LO, we are exciting other terms that will generate more harmonics and this is why the system is compressing before with lower power, because the power starts to go to other terms and not to our term of interest, that is the squared term of the ideal mixer. So this is very interesting, guys. It's a trade-off. We can have more conversion gain, increasing the LO, but we're gonna have a more non-linear system with more intermodulation, more with more harmonics. That is, in a practical perspective, it will be harder to filter the signal of interest here. We're gonna need to have a low pass filter here or a more narrow output filter. We can see this behavior also looking at the power of the second harmonic of IF. So guys, in this setup here, my IF was 10 meg. 10 meg, okay? So I entered here this circuit with 100 meg, 110 meg, and IF was 10 meg. We can see, guys, the power at the second harmonic of the IF frequency. So the second harmonic is 20 meg because our IF is 10 meg. And we can see here in the x-axis the LO power, and in the y-axis we can see the power of the second harmonic of the AF in respect to the power of the AF. So it's a relative power, is dBc. dB relative to the carrier, and in this test here the carrier is our IF frequency. So we can see, guys, that when we are inputting in the system, in the mixer, an LO power of 7 dBm, the output second harmonic is 31 dB below the IF. So the second harmonic of the IF, the spurious frequency 20 meg, is 31 dB below the IF. That is our frequency we are interested in. When we increase the LO power to 10 dBm, we increase our conversion gain. Okay, good. But now we have almost 10 dB more power at the second harmonic. So now we have a much stronger second harmonic, and as the second harmonic is very close to the IF, it's very difficult to filter it because we are only 1 octave above 20 meg. Second harmonic is 1 octave above the intercept frequency. So we can see here in dBc, in power in relation to the IF frequency, that when we increase the LO, we get less difference between the IF power and the second LO. So we can see that we can say here that as the second harmonic is increased, and as this second harmonic is a spurious frequency or spurious-free dynamic range, decreased. So now we will work with more power LO. At LO, we're gonna work with a mixer that has less dynamic range because the harmonics, the content, the frequency content we don't want will be higher. Another interesting measure we can do here is the third order intercept. Okay, and now to measure the third order intercept, we need to input two tones very close apart in the RF signal, and we can see at the output in the IF band we're gonna see the two main signals we inputted down converted, and also two side bands that are very close to our IF frequency. And this is why the third order intercept is so useful, because it's a good measure of the harmonic content, the intermodulation content that will fall inside the band of interest, inside the band very close to the IF frequency. Sorry guys. And we can see in this plot here the IIP3 input referred intermodulation product of third order, or third order intercept point, easier to say. we can see, guys, that we have at 7 dBm LO here, we have the higher third order intercept point. So 7 dBm is truly the best working power to put in the LO. When we start to increase the LO here, we can see that the third order intercept will drop. So we're gonna have more harmonic content, and this is saying almost the same thing as this plot here, and also saying almost the same thing as the 1 dB compression point. It's interesting, guys, that from a theoretical point of view, the third order intercept will be almost 10 dB above the 1 dB compression point. So this comes from the math. So, and the third order intercept will be 10 dB above the 1 dB compression point, and we can see this here, guys. The compression point when working with a 7 dBm LO is -3, as seen here in this crossing point, and -3 dB plus 10 dB will be exactly our third order intercept here. At 7 dBm, we have a 7 dBm third order intercept point. This is perfect with the theoretical math. Very, very, very interesting, guys. In reality, we can see here that the best point is 7.5 dBm here at LO. So we're gonna have an 8 dB. It's a good increase. It's a 1 dB increase in the third order intercept. But I think it's better to use 7 dBm because 7 dBm at the LO is a classical input power for mixers. And also use it as a standard for diode ring mixer also. So it's good to, I think I would use this mixer with a 7 dBm input. But we can see that all the parameters here make sense, and we can see the compression and the behavior of the circuit using the 1 dB compression point, the third order intercept, the power of the second harmonic, and really nice, guys. Really nice to grab the data from a real circuit and see that the data makes sense. Very nice, guys. So this video is 22 minutes long. Oh guys, sorry for this very long video. I hope you enjoy it. Please subscribe to the channel. If you like it, give a thumbs up, and see you in the next video.